to USACO Farms Problems stuff you know about. So what's happening here? Farm is now infinite in size. Well, that's a good expansion. So it's a 2D grid, and the cows all start in some cell. You see. And so they just sort of walk in a line, eating grass until they hit an empty cell. And then they stop. Coordinates up to 1 billion. Very big farm. Well, I suppose they're going to eat it in the grass, so really a very big thing. Oh, they only go north or east. There's no west or south cows. Okay, that's good to know. I see, but we maybe do need to figure out if they're actually gonna collide. Okay. And what is the name of this problem? Python. Okay, and these are indeed X and Y, which I'm going to label as C and R. So for each cow, you need to compute when it gets blocked. So 2 cows that are both going north or both going east can never block each other because they're going in parallel lines. Even if they started the same cell, I think they don't. They don't. So you don't even talk about it. But they would just do this. Anyway. So otherwise, they can't block each other. So maybe a diagram is helpful. Right? So we have cow I, say it's going north, and we have a bunch of cows that are going east. So some of the cows just start to the right, and then they're never going to intersect, right? Some of the cows start to the left, and so those are the tricky ones. So there's like 3 things that could happen, right? You might start to the left, and the north cow gets there first, in which case this doesn't block this cow, but of course it does block this one. You might happen to cross at the same square at the exact same time, in which case neither cow is blocked. Or you might cross over first, in which case you do block. So yeah, that's what's going to happen. And actually, I think there might be a nicer way to represent cows. I'll just use x, y. I think maybe the consistent thing to do is to use RC when thinking about indexes and x, y when thinking about coordinates. And there is no arrays or anything to index in here, so maybe x, y is better. So I'll put first the coordinate that's changing and second the coordinate that is not changing. Is that a good way to think about it? I think so. Okay, so right here we would have the y coordinate changing and x coordinate constant. So what first matters is so now we want to know how long it is from the start here to this point. Okay, and then how far up did we go in that time? And if we are then we are not blocked. We get 7 and 7, 3. North to 11. I see. Why is this happening? Oh, I see. This cow might be blocked by another one. Interesting. Huh. Problem with harder than I thought. So what are the interesting finds here? I think that just when one cow crosses the path of another, which must be right, so they cross here. That means one of them started here or here. So I think this distance and this distance are potentially interesting. myself. Let's implement the thing that only works if the coordinates are small, and then we can fix it up in case the coordinates are large. So we want to like simultaneously make them all barren after we implement this rule. Infinity 2, 5. Okay. So this should pass some but not all of the test cases, because it doesn't handle large coordinates correctly. Right, it could take like 1 billion time steps for 2 cows to intersect. So as expected, actually it passed test case 6 for some reason, even though there were no constraints, but we need to fix it for these other test cases. It would be nicer to do this. So the point is that you can set jump time forward a lot as long as there's no intersections coming up. So these are all possible intersections that could come up. And so we can jump forward time by these steps. Kind of a shame that these are not errors. 5, 3, infinity, 5. Okay, this might work. I'm not sure, to be honest. Right, but the idea is right, we have all these cows that are going in various directions. and some of them might be like super far away from intersection, but we can skip time forward by however long it's going to take for one of the cows to get the line from another cow. One of the ones that is still moving. And so that's what I'm trying to calculate. Too slow. Go. Listen. 50 cows. Is that actually correct? want to do it before or after eating? Oh. Maybe this is fine. I just submitted C accidentally. How would you get 7? No. I might have been above. Looks like it might have been above. this is a more accurate description of the rules, is that you check before you move. I don't think it should matter though. Oh, doesn't matter. So every intersection point is definitely going to be one of the original coordinates, because only one coordinate for each cow is changing. These are the relevant times. So some buffers around relevant times. If the cow has not already stopped, check if it needs to stop. Mark down that it's going to eat the congruent square. Step forward in your direction and get credit for the movement that you did. Right, so we're saying the score is the total movement rather than the total number of cells eaten, but it's the same because you don't get to eat the final cell that you move to. It's already eaten, but you do get to eat the amount in your starting cell. And then mark down all the squares that got eaten. Oh yeah, this could actually make a difference if intersect someone's starting square. What a mess. Okay. Not my best showing. So what was going on here? So I think the issue was that I was not including the terms. Actually, this might be the only relevant terms. I can use these. Yeah, okay, so I just got confused about coordinate compression. Right, so we have all of these cows going in their various directions, which are actually just north and east, and we want to know when they're going to run into each other. So I would say there's sort of two parts that I followed. One is, which is actually hinted at by the scoring. So one is just sort of do a brute force, right? Step each cow forward one space following these rules. So first you check if the square has been eaten, right? That's what it says. And if it has been, then you write down the score for that cow, which is just how many steps they've taken so far, and you're done with that cow. Otherwise, eat your current square. You don't want to actually eat it yet because there's this sort of simultaneity rule that they're both allowed to eat the same square. So just mark down that it will be eaten after you're done processing this time step. Move in some direction, and then eat all the squares that were scheduled to be eaten during this time step. And so just do that a bunch. And any cows that are still moving at the end, assume that they move infinitely. Right, so that sort of solves these small test cases. But there are also large test cases with the coordinates up to 1 billion. And so that means that it might take about 1 billion time steps for the cows to run into each other. And that's too slow to simulate, one step at a time. But we can use a trick. It's often called coordinate compression, which is that only some of the time steps are interesting. Right, most of the time the cows are stepping forward and like nothing is happening, or they're not intersecting each other. Right, they only intersect each other. Well, there's only 50 cows, and each cow only intersects each other cow once. So there's at most 50 squared intersections, and that is a small number. So you basically only need to zoom in on the times when something exciting is happening. So the way that I've handled this is I've written down a list of interesting times. So I had a bug for a long time where I was confused about which times are interesting. But which times are interesting are basically when one cow catches up with another cow's coordinates. Right, so if cow I or J was moving east, then so if you have cows like this, then this length, this amount of time is an interesting time, like this cow could intersect. And another interesting time is this amount of time, right? How long it takes this cow to get to this coordinate. And so this is the difference in x's, and this is the difference in y's, right? And those are like the two times when these cows might intersect. And so that's why we've written those down. I'm not actually certain if this is necessary. Let's try it actually. I think it might be important to like zoom in around those times because yeah, I think you would probably need the +1 at least because you need to see that you've actually apparently I'm on. No, these test cases are just not exhaustive enough. So anyway, we're zooming in around these critical times. You probably do need the +1 or at least some kind of check, like after. Like it might be enough to do this versus just a check that after everything has been done. Right. Like the point is that the last one of these might be you hitting an empty patch of land, in which case we should cut you off there instead of saying you go infinitely. So we do need at least one more check at the end. This accomplishes that. It's only a factor of 3 blow up, and it seems safer somehow. So that's what I've done. And so anyway, the idea is that you can jump forward to these times. So while there's still interesting times left to look at, figure out how long it is till the next one of those. Make sure that's at least 1. Actually, that's probably not strictly necessary. So, I see. Well, because I'm doing this fuzzing, it might be necessary, right? If the times are like adjacent to each other, I might. Well, these are sets, so that shouldn't actually happen. Oh, I see. This might hit time 0. Well, this is fine. We should simulate at least one time step. So step forward by that amount of time, and then do the simulation, except that instead of stepping by 1, you're stepping forward by dt. And so this won't actually barren out all the squares that should be, right? Because you're like skipping over a whole bunch. So only write down the grass is gone here and here. But that's fine, because you only care about the grass being gone in places where other cows might actually go. And so that's the point of picking your time steps carefully, right? You sort of zoom in around the times when cows might cross paths. So even though you're not actually eating all of the grass, you're eating all of the grass that's going to be important to any other cow. Yeah, so that's the idea. The reason this is called coordinate compression is you might think of it as right, there's like all these extra y values in here that don't really matter. And so you could imagine just ignoring them, right, and like relabel y. So like this is 0, 1, 2, and you have to remember that there's some uneven gaps in between them. But like, I mean, that's sort of effectively what we're doing, right? Is we are doing the brute force solution, but we're skipping over all of the coordinates that don't matter, or all of the times that don't matter. But you could also think of it as skipping over all of the, like literally all the x and y values that don't matter. Okay, so anyway, that is this problem, which is definitely the hardest bronze problem of the 3.